Dear children, welcome to this channel. If you like this channel, subscribe it. In the last video, we have learnt about the concept conjugate of a complex number and we did some example and exercise problems. Now in this class, let us see some additional problems on the conjugate and the next concept of a complex number, that is modulus of a complex number. Now let us see some additional problems. The first one is expressed in the standard or in the rectangular form. First problem is 2 into I plus 3 by 1 plus I the whole squared. So whatever the problem given, first what you have to do, if it exists in the fractional form, first convert the numerator to the standard form by grouping the terms, and then to come to the denominator, here also you have to make it in the standard form. Then after getting proper standard form in the numerator as well as in the denominator, then multiply the conjugate of and divide by the conjugate of the denominator and convert the whole thing in the rectangular form. So this is the way to do a problem. So here first it is not in the proper way. So multiplying 2 with I, you will get 2y plus 6. So it will be written as 6 plus 2y. And expressing 1 plus I the whole squared in the way, expanding this in the using the formula a plus b the whole squared, you will get one complex number, and then you can multiply by the conjugate of the denominator and divide by the same, and you get convert to the standard form. So here the numerator is not in the proper form, so multiply it and get the numerator in the proper form, and then multiply and divide by the conjugate of the denominator. Here no need to do it because there is no denominator, simply just a multiplication, you will get the required answer in the rectangular form. And here, so by substituting the value of I power 4, I power 9, I power 16, you will get some numerator and some denominator, and then you can multiply by the conjugate of the numerator as well as the denominator and get the value of this problem. Now come to the second one. Find the least positive integer n such that 1 plus I by 1 minus I the whole power n is equal to 1. So you have to find the value of n which gives the smallest value of n, which gives the power of this one is equal to 1. Now let us find out what is 1 plus I by 1 minus I. So the numerator as well as the denominator is in the standard form. So just multiply the conjugate and divide the conjugate of the denominator. That is, numerator will become 1 plus I the whole square, and denominator is 1 minus I into 1 plus I. What is 1 minus I into 1 plus I? Sum of the squares of the real part as well as the imaginary part. So 1 squared plus 1 squared. So I expanded this using a plus b the whole squared, 1 plus I squared plus 2y divided by 1 plus 1 is 2. I squared is 1. So 1 and minus 1 get cancelled. 2y by 2. Simply it will be I. So the value of 1 plus I by 1 minus I is I. So the whole power n is equal to 1 gives I power n is equal to 1. So for what values of n, I power n will be 1, you know that for 4, 8, 12, etc., it will be equal to 1. So among this, the smallest one is 4. Therefore, the least value n is equal to 4. The least value of n for which 1 plus I by 1 minus I the whole power n is equal to 1 is 4. Now coming to the third problem. Find the real values of x and y for which the following equations are satisfied. First one, it is given as here the right hand side is also a complex number, and left hand side and right hand side are complex number, but the LHS is not in the standard form. So rearrange by grouping the terms, arrange this left hand side in the standard form and equate the real and imaginary parts and get the value of x and y. Likewise, in the second problem, here it has two parts. The first one, the first fractional part, it is the numerator is not in the standard form. So rearrange the terms so that you may get the numerator as a standard form. Similarly, rearrange the numerator of the second one to get it a standard form. Then instead of multiplying the conjugate and dividing the conjugate of the denominator, look at the denominators. They are conjugate to each other. So just how to add two fractional parts by taking LCM. Likewise, here take the LCM 3 plus I and 3 minus I and multiply 3 minus I to this complex number and 3 plus I to that complex number and then equate it to I. So the denominator will become 3 plus I into 3 minus I will be equal to 3 squared plus 1 squared 10. On cross multiplying, the right hand side will become 10I. So now after multiplying the two complex numbers and summing up, equate the real and imaginary parts, you will get an equation in x and two equations in x and y. Solve them and get the value of x and y. Now third one is root of x squared plus 3x plus 8 plus x plus 4 into I equal to y into 2 plus I. Now here it is in the proper way, that is real plus imaginary, and right hand side is not in the proper form, so let us multiply 2y plus iy. So now it has come in the proper, that is the standard form. Now equating the real and imaginary parts. So what happened to the real part of LHS, root of x squared plus 3x plus 8 will be equal to 2y, and the imaginary part x plus 4 is equal to y. Now squaring this, we have, in order to get rid of the square root, let us square on both sides, so that you will get x squared plus 3x plus 8 is equal to 4y squared and x plus 4 equal to y. You have to solve the two equations to get the value of x and y. So instead of y, we can substitute x plus 4. So on substituting y as x plus 4, we have 4 into x plus 4 the whole square. Expand it. So x squared plus 16 plus 8x using a plus b the whole square. Multiply throughout, and then moving the terms to the opposite side, you will get a quadratic equation in x. So solve this quadratic equation using the formula minus b plus or minus root of b squared minus 4ac divided by 2a. On solving this, you will have minus 29 plus or minus root of 169 by 6, that is minus 29 plus 13 by 6. So x is equal to minus 29 plus 13 by 6 or minus 29 minus 13 by 6. That is minus 16 by 6, minus 42 by 6, minus 8 by 3, minus 7. So you get two values for x. So on substituting x is equal to minus 3, we have y is equal to x plus 4. That is minus 8 by 3 plus 4, 3 4's 12, 12 minus plus minus 8 plus 12 is plus 4 by 3. On substituting x is equal to minus 7, you have y is equal to minus 7 plus 4, that is equal to minus 3. So you get two set of values for x and y for that problem. Now coming to the fourth one. For what values of x and y the numbers minus 3 plus I x squared y and x squared plus y plus 4i are complex conjugate of each other. Here you have to find the value of x and y such that one number is a conjugate of the other. So let us take this number is the conjugate of that one. So let us consider minus 3 plus I x squared y is the conjugate of the second one. So x squared plus y plus 4i conjugate is equal to minus 3 plus I into x squared y. Now conjugate of this one is changing the sign of the imaginary part, it will be minus 4i. As two complex numbers are equal, you have to, the real and imaginary parts are equal. So equating the real and imaginary parts, we have x squared plus y is equal to minus 3 and x squared y equal to minus 4. So from these two equations, you have to get the value of x and y. From the second equation, we can take x squared is equal to minus 4 by y and substitute x squared as minus 4 by y in the first equation. We can also take y as minus 4 by x squared here and substitute here. But if you take y as minus 4 by x squared, you will get a biquadratic equation in x. But if you take x squared as minus 4 by y, you will get a quadratic equation in y. So solving a quadratic is easier than the solving a biquadratic. So that's why I have taken x squared is equal to minus 4 by y. Now on substituting minus 4 by y in the first equation, we have minus 4 by y plus y is equal to minus 3. Or multiplying throughout by y, we have minus 4 plus y squared equal to minus 3y. Or y squared plus 3y minus 4 equal to 0. On factorization, y plus 4 into y minus 1 is equal to 0. The value of y is 1 or minus 4. Now let us substitute y is equal to 1 in here, where x value can be obtained. X squared is equal to minus 4 by 5. So on substituting y is equal to 1, x squared is equal to minus 4. But if you take the square root, it is a root of negative number. Square root of negative number means it is a complex number, that is square root of 4 is 2 and root of minus 1 is I. So it will be plus or minus 2y. On substituting y is equal to minus 4, x squared will be minus 4 by minus 4, 1. So x is equal to plus or minus 1. So again here also you get two set of values. Suppose the question is, for what real values of x and y means, you have to leave this solution. as it is a complex value. But here in this question it is not mentioned the real value. Simply they have asked for what values of x and y. So you can write the solution as y equal to, when y is equal to 1, x is equal to plus or minus 2y, and y is equal to minus 4, x is equal to plus or minus 1. So both the solutions are possible. And the answers for the problem which I have not done or given, you can check it. Next, let us see the modulus of a complex number. If z is equal to x plus y is a complex number, then the modulus of this complex number z is denoted by mod z, as usual by numbers, and it is given by the value of modulus of z is given by modulus of z is equal to root of x squared plus y squared. That is, modulus of z is nothing but square root of the sum of the squares of the real part as well as the imaginary part. So, how you represent geometrically this modulus z? If you take z as a point A in the complex plane, then this OB represents the x coordinate and AB represents the y coordinate. If you join OA, then according to Pythagoras theorem, OA squared is equal to OB squared plus AB squared, that is x squared plus y squared. So this modulus z nothing. So what is root of x squared plus y squared? This is, we have defined it at modulus z. So OA represents the modulus of z. That is, geometrically, modulus z represents the distance of x of the point z from the origin in the complex plane. So geometrically, modulus z represents the distance of the point z from the origin in the complex plane. Now let us see the properties of modulus. If z is equal to x plus iy, you know that z bar, its conjugate is x minus iy. And also, you know, let us see what happens if you multiply z and z bar. Already we have seen that when you multiply x plus iy and x minus iy, it will be equal to x squared plus y squared. But root of x squared plus y squared is modulus of z. We can write it as modulus of z the whole square. So, this is a relation connecting the conjugate and the modulus of a complex number. Modulus of z squared is equal to z into z bar. Then, modulus of z and modulus of z bar and modulus of minus z always be equal. See, if z is equal to x plus iy, what is modulus of z? Square root of x squared plus y squared, sum of the squares of the real part and the imaginary part. Then, what would be z bar? X minus iy. So, what would be its modulus? Root of x squared, and imaginary part is minus y. So, minus y the whole squared. On squaring, again it will become x squared plus y squared. That is nothing but modulus of z. And similarly, minus z will be minus x minus iy. So, what would be modulus of minus z? Root of minus x the whole square and minus y the whole square. Again, x square plus y square, that is nothing but modulus of z. So, modulus of z bar and modulus of minus would be same. There won't be any change in the modulus. Then, real part of z is less than or equal to modulus of z. So, what is real part of z? X. So, x, obviously x is less than or equal to root of x squared plus y squared, because x is less than x squared, and then again x squared with y squared is added, and then taking square root, obviously it will be less. Similarly, the imaginary part y is also less than or equal to its modulus. Now, next property is called triangle inequality. So, what is it? Modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. It is not exactly equal, it is less than or equal to. Similarly, modulus of z1 minus z2 is less than or equal to modulus of z1 plus z2, and greater than or equal to whole modulus of z1 minus z2. When plus is here, less than, and when minus comes, it is greater than. So, this is called reverse triangle inequality. So, we will see the proof later. We will see the proof later after reading the remaining properties. Then modulus of z1, z2 is equal to modulus of z1 into z2. In multiplication, no inequality comes. It will be exactly equal. But in addition and subtraction, they are not equal. There will be inequalities are used here. Then modulus of z1 by z2 is equal to mod z1 by mod z2, where z2 is not a zero complex number. Then modulus of z, when will modulus of z is 0? If and only if z is a zero complex number. Otherwise, modulus of z won't be 0, as it represents a distance from the origin. Then modulus of z power n is equal to mod z to the whole power n for every natural number, for every n belongs to z. Now let us see the geometrical proof of the triangle inequality. So what is triangle inequality? Modulus of Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2. So we can prove this by even using the geometry. That is, geometrical proof of the triangle inequality is given below. Now let us consider the complex plane A, the Z1 is represented by the point A and the complex number Z2 is represented by the point B. So by the definition, OA will be modulus of Z1 and OB will be modulus of Z2. Now what will be Z1 plus Z2? By the rule of addition, if you complete a parallelogram, then the fourth vertex will be the sum of the two complex numbers Z1 and Z2. So on completing the parallelogram, the fourth vertex C represents Z1 plus Z2. So that the distance from the origin to C, that is OC, gives its modulus. OC is equal to modulus of Z1 plus Z2. But you know one property of a triangle. In any triangle, the sum of any two sides will be greater than the third side. The sum of any two sides will be greater than the third side. This is a property of a triangle. So, if you consider the triangle OAC or either OBC, whatever it may be, as it is a parallelogram, if OB is Z2, this is also modulus of Z2, and if OA is modulus of Z1, BC is also Z1. So, if you consider any triangle, either OAC or OBC, the sum of two sides, modulus of Z1 plus Z2, will be the modulus, this third side is modulus of Z1 plus Z2 is greater than the sum of the other two sides, mod Z1 plus mod Z2. So, we have modulus of Z1 plus Z2 is greater than mod Z1 plus mod Z2. Let it be equation number 1. If the points are collinear, what happens? Then modulus of Z1 plus Z2 is equal to modulus of Z1 plus modulus Z2 as the points lie on a same line. So they will be, the sum will be equal. So combining these two equations, we have modulus of Z1 plus Z2 is greater than or equal to modulus of Z1 plus modulus of Z2. So this is a geometrical proof of the triangle inequality. Now last one property is, if also the distance between any two points Z1 and Z2 in the complex plane is given by modulus of Z1 minus Z2. So, if Z1 is taken as x1 plus iy1 and Z2 is taken as x2 plus iy2, then what is Z1 minus Z2? x1 plus iy1 minus of x2 plus iy2 under modulus. So, rearranging them, x1 minus x2 plus I into y1 minus y2. So, what is the modulus of this complex number? Square root of sum of the squares of the real and the imaginary part. So, x1 minus x2 square plus y1 minus y2 the whole square. You know that this is a distance formula. So, what does Z1 minus Z2 gives? Z1 minus Z2 gives the distance between the complex number Z1 and Z2. That is, if A represents Z1 and B represents Z2, then this one gives modulus of Z1 minus Z2. This is the distance between A and B is given by modulus of Z1 minus Z2. Now, let us see the proof of triangular inequality. This is a very important question. This will be often asked. Now, what is the statement? For any two complex numbers Z1 and Z2, modulus of Z1 plus Z2 is less than or equal to Z2 modulus of Z1 plus modulus of Z2. This is a very important question. Triangular inequality. Now, let us see the proof. Consider modulus of Z1 plus Z2 the whole squared. So, you know that modulus of Z squared is equal to Z bar. So, this can be expressed as Z1 plus Z2 into its conjugate Z1 plus Z2 the whole bar. Now, Z1 plus Z2 the whole bar equal to Z1 bar plus Z2 bar. You know that property. So, you can write this as Z1 bar plus Z2 bar. Now, let us multiply Z1 into Z1 bar plus Z1 into Z2 bar, Z2 into Z1 bar plus Z2 into Z2 bar. Again, a complex number and its conjugate product will be equal to square of the modulus. So, it will be Z1 square, modulus of Z1 square. Now, let us group these two and modulus of Z2 square. While grouping, I am going to write Z2 into Z1 bar as Z1 Z2 bar the whole bar. How? Z1 Z2 bar the whole bar. This one. This is rewritten as like this. How? Z1 Z2 bar the whole bar means, as a product we can divide into Z1 bar into Z2 bar the whole bar. So, whole bar the whole bar means again the same number itself. So, Z1 bar into Z2. So, this one can be rewritten as Z1 into Z2 bar the whole bar. Now, modulus of Z1 square. So, here the complex number and its conjugate being added. So when a complex number and a conjugate being added and divided by 2, it will be equal to real part of that complex number. So we can rewrite this as 2 times the real part of this complex number z1 into z2 bar plus modulus of z2 squared. But you know that real part of a complex number is less than or equal to its modulus. So this one is less than or equal to this modulus. So replacing this, we are going to replace it by modulus, means the symbol equal to should be replaced by the inequality less than or equal to. So 2 into this one is replaced by its modulus z1 into z2 bar. Now I am going to simplify this part alone. So what would be this value? Means that I have written here equal to sign. That means that this is modulus of z1 squared plus 2 into modulus of z1 z2 bar plus z2 square will take the form here. But while comparing with the left hand side, you have to use the inequality less than or equal to. So this one is equal to modulus of z1 squared plus 2 into, as modulus of z1 z2 is equal to mod z1 into mod z2, we can write it as modulus of z2 bar plus z2 squared. Again, modulus of z bar and modulus of z are equal, so this can be written as modulus of z2. Now look at this, it is in the form a square plus b squared plus 2ab, so we can write it as a plus b the whole square. So this one has been rewritten, that been changed, converted into this one. So while comparing with the left hand side, modulus of z1 plus z2 squared is less than or equal to this modulus of z1 plus modulus of z2 the whole square. So taking square root, we have modulus of z1 plus z2 is less than or equal to mod z1 plus mod z2. So this is an important property here, and this is called a triangle inequality, and this is another important question. Now, and this result can be extended as to a finite number of terms, that is z1 modulus of z1 plus z2 plus etc. zn is less than or equal to mod z1 plus mod z2 plus etc. to mod zn. For n is equal to 2, 3 means for 2 or 3 or more terms. So that's why I have written n is equal to 2, 3 etc. So do you understand the proof of the triangle inequality? So remember here up to this equal, and here it is less than or equal to, so the equality has changed to the inequality. Again, this equal sign is equal to this. For this one I am writing this part has been equal to this one. So while comparing to the left hand side, this will be less than or equal to. Now let us see the proof for reverse triangular inequality. So what is the statement of reverse triangular inequality? For any two complex numbers z1 and z2, modulus of z1 minus z2 is also less than or equal to modulus of z1 plus modulus of z2, and modulus of z1 minus z2 is greater than or equal to modulus of z1 minus z2 under whole modulus. Let us see the proof. Here let us consider modulus of z1 is greater than or equal to modulus of z2. Now two cases are possible where z1 may be greater and sometimes z2 may be greater. So here let us, if z1 is modulus of z1 is greater than or equal to modulus of z2. In this case, let us consider z1 is equal to z1 plus z2 minus z2, adding and subtracting z2. Now taking modulus of z1 plus z2 plus of minus z2. Again using the triangle inequality, it will be less than or equal to the sum of the moduli. So modulus of z1 plus z2 plus modulus of minus z2. So what is the modulus of minus z2? Again it will be equal to mod z2. Now moving to this term to opposite side, modulus of z1 minus modulus of z2 is less than or equal to modulus of z1 plus z2. That means modulus of z1 plus z2 is greater than or equal to mod z1 minus mod z2. Let it be equation number 1. Similarly, we have the same thing if z2 is greater than z1. So modulus of z2 minus z1. We have modulus of z1 plus z2 is greater than or equal to modulus of z2 minus z1 if z2 is modulus of z2 is greater than or equal to z1. So combining these two, modulus of z1 plus z2 is greater than or equal to the difference between these two. So either it may be positive, this may be positive. If z1 is greater than z2, it will be positive, or z2 is greater than means it will be positive. So combining these two, we can write the entire thing, the difference of between these two in the entire modulus. So if in this equation, in this inequality, if we replace z2 by minus z2, what do we have? Modulus of z1 plus minus z2 is greater than or equal to the whole modulus of z1 minus of minus z2. That is plus into minus minus, so it will become modulus of z1 minus z2 is greater than or equal to whole modulus of Z1 minus again modulus of Z2. That is, then we have proved one part of the reverse triangle inequality. Now, you know that this is the result. Modulus of Z1 plus Z2 is less than or equal to mod Z1 plus mod Z2. You know it is a triangle inequality. If we replace Z2 by minus Z2, what you will have? Modulus of Z1 plus of minus Z2 is less than or equal to mod Z1 plus modulus of minus Z2. Again, it will be modulus of Z1 minus 2 is less than or equal to so replacing Z2 by minus Z2, we have modulus of Z1 plus minus Z2 is less than or equal to mod Z1 plus of minus Z2. So again modulus of minus Z2 is Z2. So we have modulus of Z1 minus Z2 is less than or equal to mod Z1 plus mod Z2. Now, so this is the statement of reverse triangular inequality, and we have proved the two results. Modulus of Z1 minus Z2 is greater than or equal to the entire modulus of Z1 minus Z2, and modulus of Z1 minus Z2 is less than or equal to mod Z1 plus mod Z2. Then, the proof for this property, modulus of Z1 is Z2 into mod Z1 into mod Z2. Now let us consider as usual modulus of Z1 is Z2 the whole square. It is equal to product of that one into its conjugate. So again product of conjugate of the product will be equal to product of the conjugates. So it will be Z1 bar into Z2 bar. Now Z2 into Z1 bar can be written as Z1 bar into Z2 as commutative. Multiplication of complex numbers is commutative. So grouping these two, Z1 into Z1 bar, we can write it as modulus of Z1 square, and Z2 into Z2 bar as modulus of Z2 square, and taking square root you will get the required result. This can also be extended to any finite number of terms. That is modulus of Z1 into Z2 etc. to Zn is equal to modulus of Z1, modulus of Z2 etc. to modulus of Zn. Next, let us see how to find out the square root of a complex number. Now, consider a complex number Z as a plus ib. So, what would be its square root? Square root of Z is equal to root of a plus ib, and let it be some complex number x plus iy, where x and y are real. That is, root of a plus ib is equal to x plus iy. So, we have to find out what would be the value of x and what would be the value of y in order to get the square root of this complex number Z. Now, how to find out the value of x and y? Let us remove the square root first by squaring. So a plus ib, on squaring it will become a plus ib, and here x plus iy the whole square. So expanding it using a plus b the whole square formula, x squared plus I squared y squared plus 2x into iy, or I squared being 1, x squared minus y squared plus I into 2xy. So the real part is x squared minus y squared, and the imaginary part is 2xy, and it is equal to the complex number a plus ib. So the two complex numbers are equal, mean corresponding real and imaginary parts are equal. So equating the real and imaginary parts. So you have x squared minus y squared is equal to a, and 2xy is equal to b. So from the two equations, you have to get the value of x and y. How to solve the two equations? Now remember one formula, a minus b the whole squared is equal to a plus b the whole squared minus 4ab, algebraic formula. So a plus b the whole squared equal to a minus b the whole squared plus 4ab. So we are going to use this by taking a as x squared and b as y squared. We have x squared plus y squared the whole squared is equal to x squared minus y squared the whole squared plus 4x squared y squared. That means a plus b the whole squared is equal to a minus b the whole squared plus 4. I have written this in the using capital A and B, otherwise you will get confused with this small a and small b. So let us rewrite this formula again. A minus b the whole squared equal to a plus b the whole squared minus 4ab. This is an algebraic formula. Then on rearranging this, a plus b the whole squared will be equal to a minus b the whole squared plus 4ab. Here in this place, instead of a take x squared and b take y squared. So what happened? X squared plus y squared the whole squared is equal to x squared minus y squared the whole squared plus 4ab. That is 4 into x squared into y squared. So if I use the small letters, means you will get confused with this small a b already we have used. So I have changed it to capital A and B. Now What is x squared minus y squared? That is nothing but a, small a. So small a squared. And 2xy is b. So 4x squared y squared will be b squared. So it is b squared. So taking the square root, x squared plus y squared equal to root of a squared plus b squared. We can neglect the negative value because x squared plus y squared being squared quantities, it will always be positive. So instead of leaving that negative value, we have taken the positive value root of a squared plus b squared. Now it is easy to get the value of x and y after getting one equation in x squared plus y squared. So already we have one equation, x squared minus y squared is equal to a. Now we got x squared plus y squared equal to root of a squared plus b squared. Let us solve these two. By adding the two equations, minus y squared plus y squared get cancelled. X squared plus x squared is equal to 2x squared or a plus root of a squared plus b squared. Then this implies x squared is equal to a plus root of a squared plus b squared divided by 2, or x is equal to plus or minus square root of a squared plus b squared plus a divided by 2. Now we can replace this root of a squared plus b squared by modulus of z. So we can, as it is modulus of z is equal to root of a squared plus b squared, this can be replaced by mod z. So x is equal to plus or minus root of modulus of z plus a divided by 2. Similarly, to get the value of y squared, take the two equation. Let us subtract it. So on subtracting, x squared minus x squared get cancelled. This will be minus 2y squared or root of a squared plus b squared minus a, or in changing that we have multiplying throughout by minus, we have 2y squared is equal to root of a squared plus b squared minus a, or y squared is equal to root of a squared plus b squared minus a divided by 2. Or y is equal to plus or minus the whole root of a squared plus b squared minus a by 2. So again, in order to avoid the confusion, let us make it as root of a squared plus b squared as modulus of z minus a divided by 2. Now, here we have x is equal to plus or minus 2 values and y 2 values. So how to get the proper value of the square root of z when x take 2 values and y take 2 values? How to arrange it properly? How to get the very exact value of the square root? Now, as 2xy is equal to b, if b is positive, then x and y should have, that is when b is positive means that is b by its modulus of b is equal to 1. Again, if b is positive means we can also say that b divided by its modulus is equal to plus 1. Then both x and y should have the same sign. That is, if x and y are positive, b will be positive, and x and y are negative, b will be positive. So when b is positive, that is b by modulus of b is equal to 1, then x and y will have the same sign. If b is negative, 1 will by x and y should have the opposite sign. When b is negative, that is b by modulus of b is minus 1, x and y will have the different sign. So square root of a plus ib is equal to plus or minus, instead of x we can rewrite it, root of modulus of z plus a by 2 plus I into this b by modulus b is given here to determine the sign, whether it is positive or both positive, or one is positive and one is negative. So I have written b by modulus of b and the value of y as root of mod z minus a divided by 2, where b not equal to 0. So according to this value of b by modulus the square root. So if it is plus 1, both the value positive, both x and y take positive as well as negative values. If b by modulus of b is minus 1, x take positive means y will be negative. If y is positive, x should be negative. So to clear this, let us give, I have given an example. So square root of minus 7 plus 24i. So according to the formula, first let us see what is modulus of z. So modulus of minus 7 plus 24i equal to root of 7 squared minus 7 the whole square is 49 and 24 square is 576. On adding this, it will be 625, that is equal to 25. Now what is b by modulus of b? b is 24. So 24 by its modulus is also 24. 24 by 24 is 1, that is b is positive. So plus or minus root of modulus of z is 25 plus a, what is a? Minus 7. So minus 7 divided by 2 plus I into this is 1. So root of 25 minus a. So minus into minus 7 plus 7 divided by 2. So 25 minus 7 is root 18 by 2 plus I into root 32 by 2. That is 18 by 2 is 9 and 32 by 2 is 16. That is 3 plus 4i plus or minus. So this will be equal to, first take, if you take plus, we have both should be plus 3 plus 4i, or if you take minus, both should be minus 3 minus 4i. Suppose if we get b by modulus of b as minus 1, you will have minus here. So when you take plus, it will be 3 minus 4i, and if you take minus, minus 3 plus 4i. So one x is positive, y will be negative, y is positive, x will be positive. So according to the value of b, this will be determined. So do you understand how to get the square root of a complex number? So you can use either this method, entire method, to get the square root, or if you remember the formula, it is very simple to use the formula to get the square root of a complex number. Hope you have understood the concept of modulus and its properties in this video. In the next video, I will solve the example problems. Already I have given some problems in the exercise as well as some additional problems. If you have not get the answer, you can ask it and clear your doubts in the comment section.